we will be carrying forward a number of things that we've learned about recently in regard to right triangle relationships and right triangle trigonometry. We want to be able to understand all of the tools that we have to be able to determine side lengths and angle measures in right triangles, and then be able to transfer those skills into a variety of applicable contexts. We want to spend a little bit of time, first of all, just building up some foundational pieces and tools that we then can apply to those more sorts of contextualized examples. So, just to recap a little bit right here, I'm going to sketch out a right triangle. And what we know to be true in any right triangle is we know some key relationships between angle measures and between side lengths. So per se, if this is our 90-degree angle right here, and we label the legs of our triangle as A and B, and then the hypotenuse of our triangle as C, one thing that we definitely know to be true in any right triangle specifically, in no other triangle is this going to be true, is that we have the Pythagorean theorem, which says that the square of the leg plus the square of the other leg is going to equal the square of the hypotenuse, right? And then also when we label the angles capital letters that are across from the lowercase side length letters, each of those angle measures have a sum of 180 degrees, as is always true in any triangle, right? So the triangle sum theorem states that the measure of angle A plus the measure of angle B plus the measure of angle C is going to be equal 180 degrees in any triangle, right? So furthermore, we also know that in right triangles, there are a number of different trigonometric ratios that we utilize. So the main first three come from SOHCAHTOA, right? And knowing that the sine of some angle is going to be able to equal its opposite over its hypotenuse, right? So I'll maybe just represent that angle as maybe like the angle theta, right? So sine of angle theta would be the opposite over the hypotenuse. So in our triangle, if our theta was maybe located at angle A, that particular acute angle, then that would make this side right here the opposite side because it's across from where theta is at. And then, of course, your hypotenuse would be right there. So in our specific example, the length of A divided by the length of C would be the sine ratio corresponding to theta, right? And then we also have cosine, which from SOHCAHTOA is the adjacent divided by the hypotenuse side length. In our particular triangle, the adjacent leg would be this leg right here, because that's the leg that is right next to our angle theta. And so in the case of our triangle, B over C would be the cosine ratio. And then we also know that tangent of theta would be equal to the opposite side length divided by adjacent. In our specific example, that would be the length of A divided by the length of B, right? So these relationships right here give us three of our trig ratios, but really there are kind of six trig ratios that we use. So what the other three are is we call them the reciprocal trig ratios because that's what they are in relationship to the first three, is that they're just flip fractions or reciprocals. And so hypotenuse over opposite instead of opposite over hypotenuse gives us the reciprocal of sine, which we call the cosecant ratio, and you need to know that. And then also hypotenuse over adjacent, which you will know is the secant ratio. And then when you find the reciprocal of tangent, we call that cotangent, and that's going to be the adjacent divided by the opposite. Okay? So those six ratios are foundational ratios that we use to be able to relate side lengths and angle measures in different right triangles. Okay? So one thing that I just want to draw to your attention about what's happening in all of these ratios right here is whenever you take one of those functions, I'm just going to say like sine, for example, you're really inputting a variable into that. So we're kind of thinking about this as being a function where you put an input and you get an output, right? So your input into a sine or a cosine or a tangent or a cosecant or a secant or a cotangent is you're always putting in an angle measure. And what it spits out is it spits out a ratio of two sides, right? So you get out a ratio of two sides, so division of two sides. Now, we are able to work backwards from those relationships as well, being able to use some relationships that we call the inverse trigonometric functions. So those inverse trig functions are known as sine inverse, which is equivalent to arc sine, and then also cosine inverse, which is equivalent to arc cosine, and tangent inverse, which is equivalent to arc tangent, cosecant inverse, which is equivalent to arc cosecant, secant inverse, which is equivalent to arc secant, and cotangent inverse, which is equivalent to arc cotangent, right? Whenever we use these ratios, I'll take, for example, just the sine inverse one, that when you put something into sine inverse, you're actually going to input the ratio, a side ratio, and what it will spit out then for you is it will spit out whatever that angle measure is that would have that ratio of an opposite to a hypotenuse that you're going to get out. And so therefore, these functions all here are inverse relationships because what we know is true about inverses is that you switch the input and output variables, right? Like you switch the x and the y. So in the context of inverse trig functions, we're just switching, the inputs and the outputs, right? So I want to look at some examples here in which we should understand some critical solving aspects pertaining to the trig ratios or the trig functions, and then also the inverse trig functions as well. So in this first problem at the far left right here, we are asked to be able to find what x is, right? Which is one of the missing side lengths. So one thing that we know is true about side lengths is if we had like two known side lengths, so if we knew what this one was, and we definitely know this is 13, we could just use the Pythagorean theorem. But we don't know two other side lengths, we only know one, so we can't really use the Pythagorean theorem. So this is where trig is going to have to kick in because we do know at least one of the acute angles in this right triangle. So if we were to reference this 32-degree angle, then that means that this side right here that we're trying to solve for is the side that is opposite to that angle. And then this side right here is the leg that is adjacent to that angle, right? So therefore, we can relate x and 13 by using some ratio that uses opposite and adjacent. And so your two choices would be either to use tangent or to use cotangent. So let's just go ahead and use tangent, which is going to be the opposite over the adjacent. So whenever you're using a tangent, you want to plug in an angle measure, which we do know. So tangent of 32 degrees would be equal to the opposite over the adjacent, right? And that's how you're going to set up that relationship right there and then just solve for x from there. So all we would need to do then to be able to get x alone is to multiply by 13. And then you'll multiply this side by 13. And so therefore x is going to be equal to 13 multiplied by the tangent of 32 degrees, right? Now that is going to be like the exact answer, but we definitely will want to try to get some sort of approximation for that. And so using a calculator then, we want to make sure that our calculator is in degree mode. So you can see that currently my calculator is not, it's in radian mode. So now I've switched it to be in degrees. And now I can type in 13 multiplied by the tangent of 32 degrees, right? And then read it as degrees. And then we can round it to, whatever, a few decimal places. I'll just go to 2. So about 8.12, right? Which is roughly about 8.12 units. And so therefore, we got what the length of that side would be, right? Okay, and then if we move to the second example here where we're solving for x, we have only one known side and we're looking for another side. So again, we're going to have to use some trig. If we reference this 57-degree angle, then 10.8 is going to be the side that is opposite right here. And then x happens to be the hypotenuse. So if we're using opposite hypotenuse, sine would be a ratio that we'd want to use since sine is opposite over hypotenuse. So sine of the angle, which is 57 degrees, would equal opposite over hypotenuse. So 10.8 over x. Okay, so now when you have the variable on the bottom right there, what you'll want to do is you can multiply by the variable to cancel out the dividing of the variable. And then, of course, you're going to have to multiply by the variable on the other side. So, of course, then we get x times sine of 57 degrees is equal to 10.8. And then to get x alone, we can undo the multiplication by sine of 57 degrees. So divide by sine of 57 degrees, it cancels out right there. And then right here, we're going to get sine of 57 degrees. So as an exact answer, x is going to be equal to 10.8 divided by the sine of 57 degrees. And then you'll want to get an approximation for that. So just use a calculator to be able to get that. And that divided by sine of 57 gives us an approximation of about 12.88 if I rounded to a couple decimal places, right? That would be the number of units for that. And then for the very last example on this slide right here, we're actually looking to be able to figure out the measure that is unknown. So actually this variable right here, which is looking for the measure of angle B, right? So we know two side lengths, one is 11 and one is 4.4. So 11 is the hypotenuse of the triangle. And then 4.4 is one of the legs, and it's actually the leg that is right next to the angle, touching the angle. So that would make this here the adjacent side. So then a trig ratio that can use adjacent and hypotenuse would be the cosine ratio, since cosine is adjacent over hypotenuse. Now we'd have to plug in the angle measure into cosine, but we actually don't know the angle measure. So we'd be able to say that cosine of theta is equal to 4.4 adjacent over 11, which is hypotenuse, right? So what we do here to be able to get the theta alone is you have to do an inverse. So we would do a cosine inverse to both sides, because then being able to plug in a cosine into a cosine inverse, they'll cancel each other out and just give you the theta alone. So theta is going to be whatever the cosine inverse of the ratio 4.4 over 11 is. So that right there would give you really the exact angle measure right there. And then use your calculator to be able to get an approximation for that. So cosine inverse of 4.4 over 11 is going to give us a degree measure of about 66.42 degrees right there. And there we would have that approximate measure for that particular angle. Okay. So carrying this even forward further here, we're asked to solve the triangle. Okay. What it means to solve a triangle is to be able to find all three side lengths and all three angle measures in the triangle. Okay? So what that means is our answer should look like this, is we should be able to figure out what is the measure of angle A, what is the measure of angle B, what is the measure of angle C, and then we also want to find all of the side lengths. So find how long AB is, find how long BC is, and find how long AC is. So we definitely know some of those pieces already, right? So we know angle A is 53.13 degrees. We know that angle C is the right angle, which is 90 degrees. And we know this side right here, C is 10, which is side AB. So 10 units, right? Beautiful. So what we do have two of is we have two angle measures. So it would be pretty easy to find the other angle measure because angle B should just be 180 because that's the total of all three angles minus 90 minus 53.13. Right. So if we evaluate that, that's going to come out to be 36.87 degrees. Okay, and so there we would have all three angle measures now. So now we just need to get the other couple of side lengths. So to be able to get the other couple of side lengths, we're going to have to use some trig to get started at least. So we'll choose one of the acute angles and maybe reference this angle right here. And then let's say that we wanted to try to solve for this side here first that I just labeled as x. This would of course be your opposite side relative to where theta is at. And then this side right here is your hypotenuse. So with opposite and hypotenuse, you could use a side ratio then to relate those couple of sides. So we could say then that sine of the 53.13 degree angle that we know is going to be the opposite side length of x divided by 10. And you can solve for x, multiply by 10 on both sides. So 10 sine of 53.13 degrees is going to equal x. Let me put that in a calculator. We get about 7.9, so it's like pretty much going to be 8, right? So we'll just round it and say that x is basically about 8 units in length. So we can say that we have that. Okay. Now you can also still use trig to be able to find this other side length down here that I'll label as y. But once you do have two known side lengths, you could just use the Pythagorean theorem as well, right? So whatever y is squared plus 8 squared is should equal 10 squared, because 10 is the hypotenuse. You want that squared alone on one side of the equal sign, right? So this would mean that y squared plus 64 is equal to 100, and then if you subtract 64 on both sides, y squared is going to equal 36. And then 36 is actually a perfect square, so you get y is basically going to be 6 units in length, right? So there we would have it, that AC is basically 6 units in length. And then we have solved the triangle, because that meant that we needed to figure out all 3 angle measures and all 3 side lengths. So we just want to look at one more of just solving a triangle. So in this triangle right here, we know side length BC is given as 15 units. We are also given side AC is 8 units. We are not given the length of AB, but since we have two known side lengths, the side lengths in a right triangle are related through the Pythagorean theorem. So since this side right here that I'll call x is the hypotenuse, then x squared alone should be equal to 8 squared plus 15 squared. And then we can solve for x. So 64 plus 225 are the squares of those numbers equals x squared. And then you can add those together. You're going to get 289 is equal to x, and then x squared, sorry. And then you can square root both sides. And then 17 is actually going to be your answer, because 289 is 17 squared. So now we've gotten all 3 side lengths. Now we just need to go for all the angle measures. We know what angle C is, that is 90 degrees, but we don't know what measure of angle A is yet, and we don't know what measure of angle B is yet. So those are actually the 2 acute angles. So what you'll want to do is just label either angle A or angle B as a reference angle. So I'm just going to go ahead and maybe label A. A is my reference angle, and then use some trig ratio to be able to find that angle. So what I might do is I might be able to reference the opposite side right here, which we know is 15 long, and then maybe this side, which is the other leg right next to theta, which is the adjacent. And so opposite and adjacent could be tangent ratio, right? And then tangent of the angle, which we don't quite know yet, would be equal to the opposite of 15 divided by the adjacent of 8. So that means then equivalently we'd have to use an inverse tangent and plug in that ratio, and then that would spit out what the angle theta is going to be, right? So inverse tangent of 15 over 8 is going to give us 61.93-ish. We have figured out that angle measure. And then once you now have 2 angle measures, you could just use the triangle sum theorem, that all 3 angles add up to 180. So therefore, the measure of angle B should be 180, subtract 90, subtract 61.93. That's going to give you 28.07 degrees. Then for that third and final angle measure to completely solve that triangle. For the remainder of this section, we are going to examine a number of different ways in which we can actually use trigonometric relationships in lots of different, more realistic contexts. So we'll begin with this problem right here. A photographer's camera has a picture angle of 52 degrees. The picture angle does limit the width of the photo that can be taken, of course. You can't just get a 360 panorama per se, right? So the photographer needs to capture a picture of a line of 12 students, and that line is 26 feet long. How far must that photographer be from the line of students in order to be able to center all 12 students in the picture? Okay, so to be able to solve this problem, being able to visualize and maybe have a picture of what's happening here is going to be really critical and really important for us. So what we have happening is we have this camera right here, right? And that camera is wanting to take a picture, but it is able to open up to like a camera angle of 52 degrees, right? So symmetrically, you've got this 52-degree angle, wide picture angle, right? So we want this line of 12 students that's going to be 26 feet long. So really all that matters there is the fact that you want to be able to capture 26 feet worth of content, right? So we want to know how far the photographer must be from the line of students, at the closest, I guess, right, in order to be able to center all 12 students in the picture. So what we could do here then is try to be able to incorporate some trigonometry into this. We don't have any right triangles directly, but if we maybe just kind of cut this perfectly in half right here, you'll see then that we do get a right angle hitting that line of students right there. So we get a couple of right triangles that are congruent to one another here. What we do know about maybe like this triangle on the right here is that now we've cut that line of students in half. So this is now going to be 13 feet since it's half of 26 feet. And then we know there's a right angle right here. And then also this angle right here that was 52 degrees has been bisected, and half of 52 degrees is going to be 26 degrees. Okay. And what we're looking to figure out is how far that photographer must be from the line of students. We're looking for what this distance is, x right here, right? So knowing one angle and one side length does make that additional side length solvable if we use a little bit of trig. So referencing this angle right here as theta, this side right here is across from it, so this is the opposite side. And then this right here is the other leg of the triangle, so this is the adjacent leg. So using opposite and adjacent, then we can use the tangent ratio. And tangent of the angle, which we know is 26 degrees, is going to be equal to the opposite on top divided by the adjacent on bottom of x. And then we can just be able to solve for x. So multiply by x on both sides, and then that means that x times tangent of 26 degrees is going to be able to equal 13, because the x's cancel out right there. And then you can divide by tangent of 26 degrees, and then enter that into your calculator to get an approximation for how long that x distance would be. So 13 divided by tangent of 26 degrees gives us about 26.65. So therefore the photographer, we need to be approximately that many feet away to be able to capture all the students in that camera image. Before we look at some further problems here, some things that we need to understand terminology-wise about what an angle of elevation is, as well as about what an angle of depression is. So when you have an angle of elevation, that would be whenever you are looking up towards something, and then whenever you have an angle of depression, it would be when you're looking down towards something. Now, what both of these have in common is they are always angles that are going to start from horizontal. Angles that start from horizontal. Okay. So what that would mean is, like, for example, you might have like a person down here, and then up here in the sky you have some like bird or something that that person is looking at, right? So, of course, the person's eyes are going to elevate and be looking in that direction towards the bird. But the important thing to understand about that is it needs to be starting from horizontal. So therefore, if the person was looking straight forward, they'd be looking this way. So when you pivot that upwards towards where they would be looking at towards the bird, this right here would be an example of an angle of elevation because of the fact that it moves from horizontal and then pivots upwards like that, right? So the opposite of that would be an angle of depression. So the bird could actually be looking down on the person, but we then need to think about it from the bird's standpoint of horizontal from the bird, first of all. So this right here would be horizontal. And then when you pivot that horizontal downwards and look in this direction, then this angle right here would be an angle of depression. Okay. So don't get that confused, because if you were to like look at, say, this blue angle right there, that's neither an angle of depression. It's not an angle of depression, nor is it an angle of elevation, because like this side right here is not horizontal; it's actually vertical, and we're never going to really use that ever when we're talking about angles of elevation or depression. Okay, so that's what angles of elevation and depression are, and they're going to be really, really helpful for us because a lot of context will talk about angles of elevation and depression. Okay. So in this example here, the traditionally accepted minimum pitch of a roof, that should just be singular, with asphalt shingles is 2 to 12. For a house that has a roof with an isosceles triangle cross section that is 42 feet wide, first question is what is the angle of elevation of that roof? And the second question is also to figure out the length of the one side of the rafter. So, what we have here is we have the pitch of the roof that is given here. So, the pitch of a roof is basically just the steepness or the slope of the roof. So, when it says that the pitch is 2 to 12, that means for every 2 units of rise, there's going to be 12 units of run. So, let's say that you have a roof like this on some sort of a building, right? So we really only be talking about kind of like one half of the roof, I guess. And so like for every 12 units of run, there's going to be 2 units of rise in that regard. Okay. Now we do know that the roof has an isosceles triangle cross section, and hence that's what this is, an isosceles triangle, because these two sides here are the same. And it's 42 feet wide, right? So if it's 42 feet wide, then from here to here, this is 42 feet. So in actuality, then, that would mean that this distance right here is going to be 21 feet. Okay. And so then we could try to figure out what this distance is, knowing that there's that ratio of 2 to 12. So a 2 to 12 ratio is the same, so it'd be equivalent to length to 21 because 21 corresponds to the 12. And so we could set up a proportion to solve for x then. So 2 over 12 should equal x over 21. And then if you cross multiply, 2 times 21 is 42. And then 12 times x is 12x. You can divide by 12. So x should be equal to that ratio. You can simplify because 42 and 12 are both divisible by 6. That gives you 7 over 2, which would be equivalent to 3.5. So then the actual measure of this height of the roof right there is going to be 3.5 feet. Okay. So then we can answer some of these questions now. So the first question right here is asking for what is the angle of elevation of the roof? So basically, what angle steepness is this roof? So that would refer to the fact that this right here is horizontal, and if you pivot upwards, then this right here would be the angle of elevation. So we're looking to figure out what that angle is. And that angle is perfectly inside of this blue right triangle, where in fact this 3.5 is opposite that angle, and then this 21 is the adjacent leg to that angle. So then the tangent of that angle should be equal to 3.5 over 21 then. So the angle itself would be the tangent inverse of 3.5 over 21. And that gives you about 9.46 degrees. That addresses that first question that was asked of us here. And then the other question that is asked of us is to figure out what is the length of one side of the rafter. So we're looking for what is the length of this side right there. And so actually, since you know that this leg right here is 3.5 and then this leg right here is 21, you could just use the Pythagorean theorem for that. And so 3.5 squared plus 21 squared, there we go, should be equal to x squared. So basically x should just equal the square of whatever 3.5 squared is plus 21 squared. So let me just enter that in our calculator. So the square root of 3.5 squared plus 21 squared gives you about 21.29 or so. So there we would have the length of that portion of the rafter then. So in Telluride, which is a very common touristy town in Colorado, there is a gondola ride that provides a spectacular view of the town and the surrounding mountains. The gondolas that begin in the town at an elevation of 8725 feet travel 5,750 feet to Station St. Sophia, whose altitude is 10,550 feet. The gondolas then continue 3,913 feet down to Mountain Village, whose elevation is at 9,500 feet. So we're looking to be able to figure out what an angle of elevation is from the town of Telluride to Station St. Sophia, and then what is the angle of depression from Stations St. Sophia to Mountain Village, right? All right, so let's see if we can try to picture this. So what's happening is from Telluride, there's a gondola that begins at an elevation of 8725 feet. So that's the elevation of Telluride. And then it travels 5,750 feet to Station St. Sophia. So we're going upwards because then the altitude at, I'll just say SSS, is 10,550 feet. So the distance of travel there is that then I guess this diagonal distance is 5,750 feet of actual cable travel, right? And then from SSS, the gondolas continue to Mountain Village, which is at a lower elevation of 9,500. So then we're going downwards a little bit to Mountain Village, which is at an elevation of 9,500 feet. Okay. So the first question that we're asked here is what is the angle of elevation from Telluride to Station St. Sophia? So we want to know what is the angle of elevation from Telluride, which means we need to go from horizontal from Telluride then, and then pivot upwards at that actual travel of the gondola and figure out this angle measure right there. So we'd want to try to construct a right triangle, so then just go straight up, so we get a nice little right angle right there, and then see if we could try to figure out that angle theta right there. So we do know this side length right here is 5,750 feet. We don't know any of the two other legs, but what we do know is the elevation of SSS and the elevation of Telluride. And so then the change in those elevations should give you the overall rise or what this distance is going to be right here. So if we subtract those two quantities of 10,550 and 8725, we get an elevation change of 1825 then. So therefore we do know two sides in that right triangle. So since this is the opposite side from where theta is, and this is the hypotenuse of the triangle, then opposite and hypotenuse would be sine ratio, right? So the sine of theta would be equal to 1825 over 5,750. And then the sine inverse of 1825 over 5750 would be equal to theta. And then inputting that into a calculator. Beautiful. And then we'll get that angle of elevation is basically about 18.51 degrees. So that would answer part A for us for finding that angle of elevation. And then we're also looking for what the angle of depression is from SSS down to Mountain Village. So since it's going from SSS, we need to start from this point right here and go horizontal and then pivot it downwards. Okay, down towards Mountain Village like this. And then look for what this angle of elevation is right here, right? So we can make a right triangle if I go straight down from right there down to Mountain Village and get a nice little right angle right here. So we do know that it did travel 3,913 feet along the cable. So this distance, which would be the hypotenuse of this right triangle, would be 3,913 feet. And then we also do know the elevations of the two towns. So if we just subtract this elevation of 10,150 with this elevation of 9,500 feet, that would be an elevation change of 650 feet between the two towns. And then we could use some trig because across from that theta would be the opposite side. And then this is the hypotenuse. So again, we could use a sine ratio. So the sine of whatever that angle of depression is would be 650 feet divided by 3,913 feet. So sine inverse of the ratio, we'll be able to determine what that angle is going to be. Oh, I had that extra plus sign in right there. Okay, there we go. So about 9.56 degrees. All right, so now in this context, we have a sun that's casting a 31-foot shadow on a tree. A person uses a clinometer, and that's a tool that you can use just to measure angles. And it measures a 70-degree angle from the tip of the tree shadow to the top of the tree. So what is the approximate height of the tree? All right, so we've got our tree, right? And then up here in the sky is the sun, and it's shining on the tree. And so when the sun comes and hits the tree, of course, it's going to be able to cast a shadow, right? So right here is going to be the shadow of the tree. And that would be something that we could actually measure, right? Because it's on the ground and humans can easily measure things that are on the ground. So this is going to be a 31-foot long shadow. And so from the tip of the tree shadow, this person is standing right here, and they measure a 70 degree angle from the tip of the tree shadow to the top of the tree. So I'm assuming that we can assume this is a angle of elevation, so a 70-degree angle up to the top right there. We want to be able to figure out what is the height of this tree. So what is h, right? So clearly this purple thing is a nice little right triangle, right? So yeah, we want to find the height. So if we reference this angle right here, the height is going to be the side that is opposite the 70-degree angle. And we know the 31-foot length is the leg that is adjacent. So opposite and adjacent can be related through a tangent ratio. The tangent of 70 degrees is going to equal the opposite, which we don't know quite yet, so we'll represent it as h, divided by 31 feet. And then we just need to multiply by 31 on both sides to get h alone. So 31 multiplied by the tangent of 70 degrees is going to equal h. That gives you about 85.17. So since that is the height of the tree, it should be in the same units that 31 was, which was in feet. So 85.17 feet then would be your approximation for that height of the tree then. We need a little bit of information about compass bearings before we can tackle some problems that use compass bearings. So what compass bearings are is exemplified as follows. I'm going to first of all just label northeast, south, and west as you've seen. So if you had like a compass bearing that said something like this, so maybe like north 30 degrees east. What that means and how we interpret that is it is going to be 30 degrees east from north. So you want to start by like thinking that you're going north and then you just change by 30 degrees by going in the direction of east. So you want to go this way in the direction of east. And so this direction right there would be what north 30 degrees east is going to be, right? So you could have something that also that goes from north, but maybe you had like north 80 degrees and then west. So then you would need to go from north and pivot 80 degrees and go in the west direction. So this right here would be north 80 degrees west. The only other like compass bearings that we're gonna encounter would be starting from south. So if you had like south and then like 10 degrees west, then that would be something like this because you would start from south and then pivot 10 degrees towards the west. Or if you had something like south 45 degrees east, then it would look something like this, where you pivot towards the east coming from south, right? Here we have that a forest ranger sights a fire that is directly to the south of that ranger. And there's a second ranger that is 7.5 miles directly east of that first ranger, who sights the same fire at a bearing of south 27 degrees 23 minutes west. How far from A, meaning the first forest ranger A, we could call them, is the fire located? All right, so let's sketch this out. So we have the Forest Ranger A, let's call them, that is sighting a fire directly to the south of them. So in this direction, everything is all up in flames over here. Right. There's a second ranger that is 7.5 miles directly east of the Forest Ranger A. So east would be in this direction. You have the second Forest Ranger, we'll call them Forest Ranger B. And they also sight the same fire. So in this direction, they can see the fire, and that's at a bearing of south 27 degrees 23 minutes west. So that would mean that from south, if we pivot towards the west in this direction by an angle of 27 degrees 23 minutes west, they would see the fire. So that would actually mean that this angle then directly is going to be 27 degrees 23 minutes in measure. And we want to try to figure out how far from A, from the first forest ranger, is the fire. So we want to try to figure out this distance right here, X, right? How far they are. Which would basically be the same thing as figuring out this distance here too, right? So we do know as well that there's a 7.5 mile distance between the forest ranger, and that would mean that this distance right here is also 7.5 miles. So if we just utilized maybe this triangle right here, which happens to be a right triangle, then we at least have a side length on it, and we know one of the acute angle measures, and so then we should be able to find x, right? So if we make this right here your theta, this side right here would be the side that is opposite that theta. This is the other leg, so this would be the adjacent side. So we could use a tangent ratio, right? So the tangent of that 27 degree 23 minute angle would be equal to 7.5 over opposite over adjacent, right? And so then to solve for x, you could multiply by x to both sides, and then you'll also have to divide by tangent of that to cancel that out, and then divide this side by tangent of that, which means that once you get x alone, x is going to equal 7.5 divided by tangent of 27 degrees 23 minutes, right? To be able to put that in your calculator, since the angle is in minutes there, you'll just want to convert that into its decimal form. So we know that 27 degrees plus 23 minutes out of 60 would give you the decimal equivalent of that. So that's really what you'd want to put into your calculator. So I can just simply do it like this. We could take 7.5 and divide it by tangent of 27 degrees plus 23 out of 60. That way it'll be just in the decimal form of degrees. And that comes out to be about 14.48 or so. And then that it gives us x, and everything is in miles. So yeah, that would be how many miles away from that first forest ranger is the fire located then. Here, the Golden Gate Bridge has two main towers of equal height that support the two main cables. A visitor on a tour boat passing through the San Francisco Bay views the top of one of the towers and estimates the angle of elevation to be 30 degrees. And then after sailing 670 feet closer, the visitor estimates the angle of elevation to the tower now to be 50 degrees. Approximate the height of that tower then, right? Okay, so we've got the Golden Gate Bridge, and pretty tall, right? So let's say that this is the bridge right here, and then out here you've got the bay where this boat is in, right? So at one point, maybe the boat is located right here, and it says that they view the top of one of the towers and estimates the angle of elevation from there to be 30 degrees. So if it's an angle of elevation, then from horizontal, we should then pivot upwards towards the top of the tower, and then have a viewing angle of 30 degrees from that point, right? And then they sail 670 feet closer, so then they move a little bit closer. So now maybe the boat is located here now, a distance that is 670 feet closer. So 670 feet apart from where they were before. And now there's a new angle of elevation. So from horizontal and then pivoting up towards the top of the tower, we have a steeper angle, of course, since they're closer, and this is now 50 degrees. It has to approximate the height of the tower. Okay, so for a problem like this, I think it would be really helpful to be able to use the two different right triangles that we're seeing in here. So for one, we have this right triangle with a 50-degree angle that I'm just going to sketch out separately for us. So we got the 50-degree, 90. We don't really know what either of the three side lengths are, but I might call this bottom side right here X. And then if I sketch out this other triangle that has the 30-degree acute angle in it, and the 90-degree, we could say that that bottom side would be an additional 670 added to the x. So this would be x plus 670 long. Okay. So we definitely would know then that if we were trying to find like the height, that this height and this height are going to be the same numbers as each other, right? And we could kind of relate those heights together with one another, because if we did use some trig ratios in the red triangle and in the yellow triangle by referencing the 50-degree angle and by referencing the 30-degree angle, we could say that the opposite over adjacent, so tangent of the 50 degrees, is equal to h over x from the red triangle. But then from the other triangle, we could do the tangent ratio of the 30-degree angle and then get h over x plus 670, right? So solving this one here for h alone, then x times tangent of 50 degrees would equal the height of the Golden Gate Bridge, right? And then solving this one for h alone, the quantity of x plus 670 multiplied by the tangent of 30 degrees would equal h alone. And because we know that that h and that h are alone, we could take this quantity and this quantity right here and set them equal to each other because they're going to be the same heights, right? So then we can say that x tangent 50 degrees is going to equal, and then I'm going to distribute the tangent 30 to the x, and then the tangent 70. And so from this equation, then, we should be able to figure out what x is going to be. So we will need to get this term and this term to the same side so that then we can actually factor out the common factor of x from them. So x tangent of 50 degrees minus x tangent of 30 degrees would equal 670 tangent of 30 degrees. And you can factor out the x. So then tangent 50 minus tangent 30 is inside of the parentheses. And then you can get the x alone if you divide by that subtraction of the two tangents right there. Cancel that all out. And do the same thing right here. And then you can divide by tangent of 50 degrees subtracted by tangent of 30 degrees. So that should give you what x ultimately is. So if I input that into a calculator, 670 tangent of 30 degrees. And then we need to divide that by, so I need parentheses so that I make sure that the tangent of 50 minus the tangent of 30 all gets divided by here. And then we get that approximation for what x would be, so about 629.59. So now we figured out what x is, which is what this distance is right here. So we still need to figure out what the height of the tower would be. So we could go back and plug in x into these couple of triangles that we have. It would probably be just easier if we just use the red triangle. So now in that red triangle, now that we know that x right here is going to be 629.59 degrees, then from knowing that from over here, that the height is going to be x times tangent of 50 degrees, then you can evaluate what that height is going to be, right? I don't know why I put degrees on this 629.59. It's a length measure. Okay, so 629.59 times tangent of 50 degrees should give you the height of the tower then, which is about 750.32. That would be in feet, since everything was in feet, and gives you the answer for that particular question. When a watcher is on a ladder and looks at a nearby building 100 feet away, notes that the angle of elevation to the top of that other building is 18.7 degrees, and the angle of depression down to the bottom of that other building is 6.5 degrees. We want to determine how tall that other nearby building is. So, sketching this out, you've got this window washer that is currently washing windows on some building. So, of course, the ladder is going to be leaning up against the building. And then at the top of the ladder, right there, is the window washer currently, right? So, 100 feet away from where that window washer is, so from the other building to the other building here, we've got this distance of 100 feet apart. And so the window washer is looking upwards at an angle of elevation. So that means that from horizontal eye level of the window washer and then pivoting upwards, they're seeing the top of the building, and that angle there is going to be 18.7 degrees. And then we also have that an angle of depression. So from horizontal and then pivoting downwards at an angle of 6.5 degrees, they can see the bottom of the building. We want to know how tall that other nearby building is. So what is this overall distance right here? So I think the way that we can tackle this is we could try to figure out what is this distance right here that I'll call x, and then figure out this distance right here that I'll call y, and then just add them together and look at the overall height of that other building. So to be able to get x, we could use this right triangle that we're seeing right here. If we reference the 18.7 degree angle, we'll see that x is the opposite side. And then we also know that this distance right here, that is the adjacent side, is going to be 100 feet, because that's the distance between the buildings. So x over 100 would be the opposite over the adjacent, which would be the tangent ratio. So tangent of 18.7 degrees would equal x over 100. So x is going to be 100 times the tangent of 18.7 degrees. Which is about 33.85. And that'll be in feet. And then similarly, to be able to find y, we can reference this 6.5 degree angle. Y is going to be the opposite side. And then we also know that 100 is the other leg, which is the adjacent. So we also know that tangent of now the 6.5 degree angle would be the opposite of y over the adjacent of 100. So 100 times the tangent of 6.5 degrees is going to equal y. Which is about 11.39. feet. And then from all of that, then we can just add x plus y together to be able to get an approximation for the overall height of the other building, which gives you a sum of about 45.24, and would approximate the height of that other building then. Here we have that a vertical antenna is mounted atop a 50-foot pole from some point that's on the ground 75 feet away from the base or the bottom of the pole. The antenna subtends an angle of 10.5 degrees. And then find the length of what that antenna is that's atop the pole. So here we could construct a little sketch of our 50-foot pole. And then on top of that is some antenna that we want to try to determine the length of. And then from the bottom of that pole along the ground, 75-foot distance, we've got this subtending angle. So what that subtending angle means is that if we were to find the angle of elevation up to the top of the pole right there, and then compare it with the overall angle of elevation to the top of the antenna, so meaning comparing this angle measure to this larger angle measure, there would be a difference of 10.5 degrees. So then we would know that this angle only in the orange right there is going to be our 10.5 degree angle. Okay? So we want to try to find the length of that antenna. So what would be really helpful to find that length of the antenna is to be able to just maybe try to figure out this whole side length right here, which we could do if we could do some trig with the overall larger right triangle. But we don't know what that whole entire angle is down here, so this darker blue angle. But hopefully we'd be able to figure out this lighter blue angle because in this smaller triangle right here, we do know two of the side lengths there. We know that that yellow triangle has a side length of 50 feet for one of its legs and 75 feet for the other leg. So if we were to reference this lighter blue angle right here as theta, then opposite and adjacent would indicate we could use a tangent ratio. So tangent of theta would be equal to 50 over 75. So tangent inverse of 50 over 75 would give us what that lighter blue angle would be. Which would be 33.69 degrees approximately. And then once we know that that is 33.69 degrees, we would know then that for this larger right triangle right here, that the overall angle we would have now is 10.5 degrees greater than 33.69. So 33.69 plus 10.5 is going to give you 44.19 degrees right there. And then we could figure out what this overall side length is right here that I'll maybe just call x by using some trig because we know that this bottom side length here is going to be 75. So we would use tangent again because we're relating the opposite over the adjacent. But now tangent of 44.19 degrees will equal that. So 75 times tangent of 44.19 degrees is going to equal x. Should be about 72.91 then for x. So x is about 72.91 feet. And then once we know that this overall distance right here is 72.91, 50 feet of which is the pole, then the rest of that would be the antenna. So if you just subtract 50 from 72.91, it's going to give you 22.91 feet, which of course would be then the height of that antenna.